Welcome to the Femap version 11 What's New video series. In this video we'll be looking at how to generate external superelements in Femap and then see how they can be used in a subsequent assembly run. Superelements were initially developed and used as a means of substructuring a finite element model into more manageable pieces for analysis. However, another use for this technology is the external superelement, which allows transfer of model characteristics like stiffness and mass from one company to another without including the finite element model detail. External superelements are largely used to transfer dynamic modal characteristics, but can also be used for statics, which is what we'll use to demonstrate the capability here by transferring an external superelement of the winglet model to a completely separate wing model. In the winglet model, a side pressure loading has been applied, and all that remains is to set up the analysis manager to create the external superelement. In the analysis manager boundary conditions definition, there is a constraint set which will act as the boundary or A set for the external superelement. However, for the external superelement creation, the constraint set should be set to none. In the external superelement dialog, we'll set the superelement ID, select the required output matrices for the statics run, set the output to OP2, and apply a file name. Then we select the output method for the additional bulk data required for the subsequent assembly run, and set the master ASet. While this is a statics run for a modal analysis, Femap can create the additional degrees of freedom on the fly that are required for the Craig-Bampton approach for component mode synthesis. In general, when exchanging model data using superelements, there is an agreed node and element numbering scheme for the different components of the model, and this dialog allows ID range checks to be performed. In this case, the external winglet superelement connects to node points that actually exist on the wing model, and as such belong to a different ID range, which is why the node ID range is flagged red. With the dialog completed, Femap uses this information to write out the necessary assign and ext_seout nastran statements. Now we can set the analysis running to produce the external superelement files. The resulting OP2 and ASM files can then be transferred to the wing manufacturer for the assembly run, where the winglet stiffness and load matrices can be attached to the wing model. Now, within the wing model, we can attach the winglet as an external superelement. Here we've set up a dummy load to activate the external superelement loading, that is the winglet side pressure load. A constraint set has already been defined, so all that remains is to set up the external superelement reference in the analysis manager, that is to pick up the OP2 file, set the unit ID, and reference the ASM bulk data file. For the winglet boundary nodes, we can set a more lenient duplicate node tolerance. As before, with this input, Femap will automatically create the required nastran assign statement. Finally, to address the external superelement loading, we'll manually add a seload entry into the bulk data. Then we can run the assembly. Once the analysis has completed, we can review the results, which in this case are solely due to the pressure loading on the winglet. Zooming up on the tip of the wing shows the effect of the winglet external superelement loading. Using external superelements, it's possible to transfer model data completely confidentially, as none of the geometry or finite element model detail is transferred. To find out more, visit us at siemens.com/plm/Femap or call your local channel partner.